Hi, welcome back to Kine 3030 Online. Today we're going to talk about balance and stability, but first we're just going to do a quick review of static at the equilibrium at the joint level, and I left you with this question. That you have that client who was doing biceps curls using the bands, so basically this. And yet they were worried about their shoulder. It was aggravating. And you need to figure out which muscle group is active at the shoulder, if any, and by how much. And you should always start with an appropriate free body diagram. I've given you the information about the mass of the client, and what percentage of the client would be, of their total body weight, would be the segment weight, which is 5%, 0.05. The actual force coming from the resistance band is 15 newtons, and it acts 70 degrees to the horizontal. And we have a distance from the moment arm band to the shoulder of 15 centimeters, and a location of the center of gravity of the arm, which is from the arm to the shoulder would be 15 centimeters. Or sorry, 5 centimeters. Apologize, 5 centimeters. So, this is the free body diagram of the segment. Again, if we want to figure out what's going on in the shoulder, we cut through the shoulder, right? Cut through the shoulder if you need to figure out what's going on in the shoulder. And then we look at either everything distal to the shoulder, which would be the whole arm, forearm, hand, and upper arm, or it would be the rest of the body except for the arm. And it's easier to go distal, so it's easier to go with the arm, because then we don't have to worry about what the ground reaction forces are, etc. And that's just how we typically do it. And you can see here we have the weight of the arm, we have the force of the band showing there, we have the two reaction forces at the shoulder, the X and Y components of those reaction components, and then we have the torque. We're just trying to figure out the muscle torque here, because we don't know exactly which muscle group it is. Is it the flexors or is it the extensors? Do you know that ahead of time? And if you don't, then you have to start with just a torque. And as I've drawn the torque right now, you could see it would try to bring the arm up this way, which means as I've drawn it right now, if I get a positive value for that torque, we have a flexor torque. Okay, I've put some dimensions in there. So, first of all, we need to figure out the weight of the arm. Weight of the arm is the mass of the person times the fraction of the whole body weight, total body weight, that is the arm. That's the 0.05, and times, of course, 9.81 to make it into a force. So 34.3 newtons. Now we are going to try and figure out the torque around that shoulder, so what it is. And if you have some sort of band of this nature at home, try it and figure out where you feel it. Where do you feel it? Which muscle group do you think it's going to be? And do you really feel it in the shoulder? Like, I mean, would this be a shoulder activity? And I'm going to tell you, yes. Yes, you are going to feel it in the shoulder. So the sum of the torques around the shoulder equals 0. We're assuming that it's, you know, kind of held in place, making it a static activity. So we have the, if again, counterclockwise, I'm considering positive. So I drew my muscle torque at the shoulder as counterclockwise just because I wanted it to be flexor is positive, and as I've drawn that free body diagram, it just turns out that flexor positive would be a counterclockwise direction. And then I have the weight of the arm times its moment arm, which is 0.05, and that would be negative because it would try and rotate my arm the other way. The weight of my arm is going to try and pull it this way. Same with the force at the hand, which is 15 newtons times the 0.15. And again, negative because it would also try and pull my arms down. And so it would try to extend them in that posture at the shoulder. So from that, you can solve for the torque at the shoulder, which would be 3.97 Newton meters. So it's positive 3.97 Newton meters. It's a positive value. As I've drawn that, a positive value would be my flexors. And again, try it and see where you feel it, but you should feel it in your shoulder flexors. We can also figure out the joint reaction forces. Again, these will not be as large as the actual bone-on-bone forces in the glenohumeral joint because we are using the torque approach, and the net torque approach does not include the force of the muscle, so it underestimates that the actual forces in the shoulder, but it gives you a first pass. And so sum of forces in the x direction equals 0, and that's going to be the joint force in the x direction minus the force of the band in the x direction. And that's where you're going to have to use that cos 70 because the 70 degrees. So in the end, you're going to have 5.13 newtons in the x direction, and in the y direction, you have the joint force in the y direction, positive as I've drawn it, weight of the forearm and hand and upper arm. So the whole arm, weight of the upper arm as a force, which of course is down, so it'll be negative. And the force of the band, which is also down in the y direction, and that'll be the 15 newtons times the sine 70, so it's the component that is down. When I rearrange that, I am going to come up with 48.4 newtons in the joint force in the y direction. So that's how you solve that, and that's an example of the equilibrium at the joint level where we can find out. That's a torque example. If we knew strength of torque, strength of the shoulder flexors for either the client or for a population that might include the client, you could then figure out what percent MVC they were working at. So now into balance and stability, where we're going to, again, we're going to define stability and understand the factors that affect it and understand the strategies we will use to improve it. So what can a wrestler do to prevent being pinned? So basically, they want to stay upright. They don't want to get down if they can help it. So we'll come back to that one. Stability. The capacity of an object to return to equilibrium or its original position after being displaced or perturbed is another word you'd hear for that. Static equilibrium, of course, is that situation where there is no acceleration and the sum of the forces equals equals 0, and the sum of the torques equals 0. And balance is the ability for us to control our equilibrium. So there's a lot of forces or sports that require high stability. The main ones, these are examples of ones: wrestlers, football linemen, an elderly person walking. Why? Well, I think you can see these are sports where you don't want to be tipped over. You don't want to be, you want to stay upright. You want to stay involved. And certainly the implications if you go over are high. An elderly person walking, if they fall down, they can, obviously the implications are high. That's when you get your hip fractures. So it's the importance of not losing it and the difficulty in maintaining. On the other hand, we have the sports where less stability can be good. These are examples: sprinters, swimmers at the start, downhill skiers, soccer goalie. Well, the reason is because we're often at the edge of stability in order to get a quick start, in order to change directions quickly. So we're trying to do things by staying right on the edge. We can make movements quicker. So, if we're looking at somebody who is going to lose their balance, and what does that mean? It means to be balanced, your center of gravity is within your base of support, okay? And unstable means that your center of gravity is either outside your base of support, in which case you're going to fall, or near the edge of your base of support, which means it would be easier to put it outside the base of support, in which case you will fall. Now, fall doesn't necessarily mean that you're going to land on the floor. It might mean that you have to take a step or change your body posture in some way to react to it so you don't fall. So we remember what a center of mass is of the whole body. That's we're looking at the whole body, so it includes all of the different body segments together. And the base of support is the area around the outermost regions in contact between a body and support surfaces. When we're talking walking on flat surfaces or doing things on a flat surface, that literally means the area that our feet or our hands, depending how we're doing, are in contact with the ground. In the event that there's something else that we can grab onto, that actually would include our base of support, because now we have something up here that we're holding on to that is increasing our base of support. There are a number of factors that affect stability. We have Newton's first two laws, and we're going to see how that's important. We have the actual base of support. We have the location of the center of gravity with respect to that base of support. We need to talk about what the height of basically the height of the center of gravity is, and what the weight of the object is, person or something else. The potential energy, we want to minimize the potential energy, and I'll get to that. And we have to remember, in the case of humans, we do have that neuromuscular system. We have control over things, so we can modify where our center of gravity is within our base of support. So, think about Newton's laws with respect to an angular situation. A rotating body will maintain a state of constant rotational motion unless acted upon by an external torque. And also we have, of course, the sum of torque equals I alpha. And basically, an object is going to maintain its stability unless it is acted by a torque. That's really what it comes on to. If I'm standing here doing nothing, then I'm going to stay pretty stable unless some sort of external torque acts on me. So if we push an object over, it really is an active rotation. See that? It's an active rotation to tip something over. You are actually rotating it around the outer side, on the side that it's going to tip over. And if we're going to prevent the rotation, then the torques must be balanced. In other words, the sum of the torques equals 0. Okay, so let's think about the book. There we go. And if I'm going to push it over, you can see it's going to rotate on that edge. It's essentially a rotation around that edge. And the distance from the table up to where I'm pushing, and I'm pushing horizontally, so that's going to be the moment arm of the force, of my pushing force. And at the same time, we have the weight of the force for the weight is going down the center here, and its moment arm is literally that width of where that center of gravity is with respect to that side. So, in the end, if you have the sum of the torques right now, it's in equilibrium, and if we want it to remain in equilibrium, that means the torque created by that push, which is this distance times however much I'm pushing by, is going to be the same as the force down, which is the weight of the book, times its moment arm, which is quite small in this particular case. And if you look at those four factors, how much I'm pushing, how high up I'm pushing, the weight of the object, and the distance from where the center of gravity is to that outer side of the base of support, you are essentially going to get the four factors that really talk to the things that affect stability and balance. So you need to keep this, the push times its moment arm, to be less than the weight times its moment arm for this not to tip over. As soon as the push times its moment arm, the torque created by me pushing on this book, exceeds the weight by its moment arm, the book is going to fall down. In other words, you want to minimize this guy and maximize the torque created by the other one. So let's start with the base of support, which is really maximizing B. And the base of support is the area around the outermost regions of contact, as I said. In a horizontal projection of the center of gravity moves outside that base of support, you are going to lose your balance. And the wider the base of support, the increasing the stability, because it's just farther to push my center of gravity to an edge than it is if my feet are close together. So if a force comes this way and my feet are close together, it doesn't take that much to tip me over. Whereas if I'm like this and the force comes, I have a greater area that I will cover before I fall over. And that is the B portion of that, of the equation that we've been talking about. What does that mean? So there's some pictures of base of support, and you can see the line around all of the different places that are in contact. If I was just on one foot, it would literally be a line around my shoe. If I've got one hand down, it's going to be that triangle. If I have a cane in my hand, it's going to be a triangle that's going to include the cane. So you can now understand why walkers are so beneficial for elderly people who do have balance issues, because it widens their base of support. We want to know where that location of the center of gravity is within that base of support. And the closer it gets to the edge, the easier it is, as I've said before, to tip over in that direction. Now, you can actually play with that in order to increase your stability if you position it towards an oncoming force or towards the base of support on the side that you aren't likely to be tipped to. So if I'm going to be tipped this way, if somebody's pushing me here, it's going to tip me there. It's going to be, then if I move my base of support over here to begin with, I have an advantage. Again, it is the B. The distance between that center of gravity and the edge of the base of support is the B on the side that we're going to tip towards. So again, this is widening our base of support. You have two people there, the same weight. Two examples, it's the same person, same weight. One with wider legs, one with narrower legs. And you can see from where the center of gravity hits the ground to the edge of the base of support is bigger with the wider legs. So if somebody's pushing me, it's harder to move my center of gravity over to the edge in the first one than it is in the second one. And I can even increase that by moving towards which direction that force is. So in all three cases here, they have the same stance, but in one case, they move their center of gravity to one edge of their base of support, and in the other to the other side of the base of support. So in the middle one, they've gone to this side, and if the force comes this way, it doesn't take much to tip over, right? Oh, sorry. There's just not much to move you there. Whereas if the force comes the other direction, so if I'm here, I'm on this side and the force comes from this direction, I have all of this distance that I can move, okay? And so if I move my center of gravity towards the side of the base of support that the force is coming from, then I have a lot greater motion to be able to handle. So that is the B portion of the base of the distance between the projection of your center of gravity on the ground and the edge of the base of support. Next one is W. So remember, B times W is the torque created by the center of gravity, by your weight itself. The torque created by your weight around the edge of the base of support that you're going to tip around. I want to maximize B times W. I can maximize W or B. We've just talked about ways to maximize B. I could also maximize W. I can increase the weight. So something that is heavier is going to be harder to tip because it maximizes that piece. If all else is equal, if everything else about a situation is equal, but one, so they're the same shape, the same height of the center of gravity, same base of support, and the weight is greater in one object than another, one person than another, and it's going to be harder to tip over the object or the person with the greater weight. Reducing the height of the object, well, that has several factors. Number one is, so all being equal, i.e. they have the same base of support, the shorter object is going to be one that doesn't allow as high a push. Remember, we want to minimize the push force. We don't always have control over that if that's coming from somebody else. But the other thing we can minimize is where that force is actually pushed on us. And for something that's shorter, or if you crouch down like this, then the highest that force can really be is this level. I suppose it could push on your head, but you would hope that isn't the case. Whereas if I'm standing upright, they're pushing here. So it's easier to tip over here than it is here. Be tipped over by an external force. The other thing is that the shorter situation, so if you're in that crouch, your center of gravity is going to be lower, right? Your center of gravity is lower. And as I will show you later on, that has implications in terms of potential energy and makes it harder to tip something over. So if something has most of its weight down near the bottom, then it is typically harder to push over than if the weight is up high. And that's, again, because of this minimizing the potential energy. Potential energy is the energy associated with position off the ground. It's energy associated with gravity. So if I have something here and let it go, it's going to, gravity is going to pick it up and increase its velocity and give it energy. Okay. It doesn't have any kinetic energy when I'm holding it here, but as soon as I let go, it will increase and it will have kinetic energy that'll keep getting more and more. Kinetic energy being the energy of velocity and motion. So we have potential energy, which is the energy associated with the position off the ground, and it is equal to mass times the distance off the ground times g, 9.81. The closer the center of gravity of the object is to the Earth, the less potential energy it has. And to raise it requires energy. So if I raise something from here to here, I have to actually give it energy because it has so much potential energy here and it has more potential energy here because it's higher. So when you topple an object, it requires that center of gravity to go up and over and then comes down. Just think about that in a box, and I'm going to show you some pictures of that. So The yellow one is something that is a low center of gravity. And imagine that I'm pushing on it from the right side. So you see the box sitting there. And when I push on it from the right side, it's going to rotate around the left corner. And as it rotates, the radius, the distance from that corner to where the center of gravity is that line there that you see is affected by, that affects that DH. And as I rotate it around, because my radius is smaller, the height difference between when it's lying flat and when it's tipped over on its side, or on its corner, that's going to be that change in dL, L being the low center of gravity. Okay? Now, when my center of gravity is higher, the radius between where it is on the corner and where the center of gravity is actually going to be longer. And to be honest, when you tip it over, you are not going to have as much of a change in the height anymore. So that's that delta DH. So that's the change in the height of the center of gravity, and it takes energy to raise the height of the center of gravity. So when you push on the low box, you have to raise the center of gravity more than you do if you push on the high center of gravity box. And with that one, you only change that center of gravity a little bit in order to topple it over. In other words, it does not take as much energy to topple the one where the center of gravity is high as it does for the one where the center of gravity is low, all else being equal. And finally, yes, we're not static. We can move, we can change where our center of gravity is, we can change our base of support. And it's a huge area of research. It's an absolutely huge area of research, that the effect of posture and balance and things that affect that. You can stand on a force plate and see how much we sway and how that is affected by having your eyes closed, having vestibular problems, different types of perturbations. So are you pushed, or are you leaning against something and then it's released? There's a number of different ways we can perturb the body, and we learn a lot about how our brain controls both takes all the stimulus in and then controls the muscles in order to modify our position and allow us to remain balanced. Big area of research. So if we come back to our original problem, what can a wrestler do to prevent being knocked over? Well, let's start with, if you think through that list that we talked about, let's actually start with that one at the bottom, increase the mass. Can we increase the mass? Well, no. We can't increase the mass on a instantaneous, in the moment scenario. When we're in the actual competition, our mass is our mass. Certainly, you all know that there are weigh-ins and that different elements, different people of different weights compete together. And they have a weigh-in to decide which weight class you are in. What you want to do is you want to be at the top end of whatever weight class you are. So let's, if you are normally, and this is actually a problem, not really biomechanically, but it can be a problem with people with food control issues, but and certainly we know that there's a large amount of fasting that can occur just before the weigh-in, so that you drop your weight to just under the top end of the weight class, so that you are you don't want to be the one at the bottom of your weight class. Just unfortunately the way it works biomechanically to give you the most advantage. But once you're already in a weight class, there's not much you can do about the mass piece. At that point, it's a done deal. So now, what kinds of things we can do? We can crouch lower. We can crouch lower, which have two effects, and one of them is that it lowers our center of gravity, which, as we've talked about, makes it more difficult to tip over, everything else being equal. It also means that whatever handholds your opponent can get on you to try and flip you are going to be lower, because if you're standing up high, they can grab something high, but if you're down low, it's going to be down low. We can increase the base of support in the plane of the force application. Now that's important, and you might not know. That's the one thing that is problematic. Do you know, are they going to pull you or push you? So that would be in the frontal plane, or are they going to try and tip you over sideways? Often you'll see something like this, where you have a little bit that is forward backwards and a little bit that's sideways. But on the other hand, if they are, you do open yourself up there for something that is a pull on the angle. Okay, so you have to sort of predict which way they're going to pull you based on, and which hand they're going to grab you with. And then you're going to need to lean in to the direction of force application. So if you are going to be pulled, then you want to be back. Okay, if they're going to pull you forward, then you want to be back, because that gives you a lot more space here for your center of gravity before you're over the edge. If you don't know which way it's going to be, then you have to be in the center. Okay, because that's that gives you the most in both directions. So just to review, we have stable and unstable systems, and unstable really means that our center of gravity gets outside that base of support. And understand those factors that are going to affect stability, that width of your base of support, the location of your center of gravity within the base of support, the height of the center of gravity, and the height direction of the potential push-pull forces, the mass, and then the ability to control things.